Okay, this is our very last lesson for the whole entire year. So once you're done with this, you're done with all the assignments for the year. We'll just be moving on to our review for midterm 3 and then review for the final. So today we're going to find parametric descriptions for oriented curves. In other words, I'm going to give you parametric equations and we're going to kind of convert them back into Cartesian. And some vice versa. So recall that we had that several curves in the examples from the last section resembled graphs that functions we've seen before. We look at examples, eliminating the parameter to determine a Cartesian equation. So this is actually one example that we had last time, and it gives us this graph over here on the right, which is a parabola. So the idea behind eliminating a parameter is we want to solve one of these equations for t. So we have x equals t minus 1, and we've got y equals t squared. The easier equation to solve for t is probably this first one. And the way that I would do that is if we had x equals t minus 1, let's add just 1 to both sides. So we get t equals x plus 1. Once we have that, we can use our idea, like solving a system of equations, of substitution, and we're going to plug that in for t. So we get y equals x plus 1 squared. And you'll notice right there that is the format of a parabola, right? It's shifted 1 unit to the left, x minus 1, which is what the vertex looks like over there, shifted 1 unit to the left. So that is the equation you're given. Okay, on this next one, eliminate the parameter t. So you want to look up here. In this case, having t in the exponent is probably not going to be the easiest place to solve for. So in general, if you have something that's linear, I would solve that one for t. So we're going to solve that second one for t. So y equals 1 minus 4t. So we're going to subtract 1. So y minus 1 equals negative 4t. And then divide both sides by negative 4. At this stage, we now have t equals y minus 1 over negative 4. You can leave it like that, or if you prefer, you could call it like negative y over 4 plus a fourth. Like those are equivalent fractions, right? Whatever you prefer. But in this case, we're going to take what this value of t is, and we're going to plug it in to where t is in the second equation. So this time x equals 2e. And I'm going to leave it as that first fraction, so y minus 1 over negative 4 is the exponent. But that is still a Cartesian equation, so we're good to go. Okay, example 3 is not as easy, right? In this case, you can probably recognize it as half a circle, right? Because there is some limitations here. So in this case, we are going to go ahead and we are going to look or kind of use some of our knowledge that we've had in the past of what a circle looks like. So, as we take a look, we're going to go ahead and think about if x equals cosine of t and y equals sine of t. Use your the Pythagorean theorem identity. So we get cosine squared of theta plus sine squared of theta equals 1. We're using something that we know that is true. So in this case, if we let theta be t, we'd have cosine squared t plus sine squared t equals 1. But what is cosine of t the same as? That's the same as x. We'd have x squared plus sine of t is the same as y, so y squared equals 1. In this case, we have that unit circle, and that is what we get. In this case, you could limit technically x is from 0 to 1, and that would give us such that we only have the right half of the circle, but I'm not going to worry about that right now. Okay, so now let's look at parameterizing curves. So we're going to write parametric equations for each Cartesian equation by setting either x equal to t or y equal to t. When you set x equal to t or y equal to t, you want to look for the easiest one. So in this case, like if I set y equal to t, like y equals t, then all of a sudden I'd have t equals this whole thing, and we'd have to figure out and solve for x. That's going to be a little bit harder. So look for the equation that's not already equal, like x equals or y equals. So in this case, if I let x equal t, then I can just rewrite this second equation, y equals 3. Rather than x, we're going to use t squared plus 3. And this would be our parametric equations. On this one, since it already is x equal, we're going to use the opposite logic, right? So we don't want to set x equal to t, we're going to use y equal to t in this case. So this time if we have y equals t, the second equation, x would equal 3 log, rather than of y, of t plus y, which is also t here. We've got our parametric equations. Okay, easy enough when it's like that, but what if we have some of our conics, right? It's like in a circle, or we'll talk about another one as well. So, I had 2 example 4s, that should be just example 5. Write the parametric equation for each Cartesian. This time you're going to have x equals a cosine of t or y equals b sine of t. So let's just think about this for a second. This is really similar. We know x squared plus y squared equals 16 is a circle, right? Specifically a circle with radius of 16. You could think about it though if you wanted though. We could divide both of these by 16. So we'd have x squared over 16 plus y squared over 16 equals 1. The fact that those are equal is what makes it a circle. So we usually write it in that format up above. So let's just think. So x equals cosine of t. We've done that in the past. Y also equals sine of t. Sorry, y equals sine of t. The numbers out front represent the radius, right? So in this case, the square root of 16 equals 4, so we've got a radius of 4, and it's equal for both of these. So these are my parametric equations. The other way to think about it is we look at this next one, the fact that we have x squared over 4 plus y squared over 9 equals 1. This time, rather than this one's a circle. This one, we do not have it equal on both sides, so it ends up giving us an ellipse. Good review from 1050 there. X will still be sine of t, y will be cosine of t, but this time, if we think about under x, what will that number be, or that a value? We get the square root of 4 is 2. So in this case, a equals 2, and b is going to be the square root of 9, which equals 3. Okay, last but not least, we want to find some of these for 2 different things. We're going to do a directed line segment, and then we're going to do a circle that's a little bit adjusted. So the directed line segment from 3 and negative 5 to negative 2, 2. So the way they talked about this in the textbook, they actually gave you an equation, but I think it's easier to maybe say it in words. Like the equation they give is like x equals x naught, and then like x1 minus x naught times t, right? But the way to think about it is, hey, if we want to talk about what's happening to these x's, right, and we wanted to come up with like how you get these different x's, we are going to start with our initial x, which in this case is 3. Think about that as your starting point. But we want to end at negative 2. So how do I get from 3 to negative 2? Well, I'm subtracting 5. So we're going to do 3 minus 5t, meaning, hey, the first point is at 3, but when I subtract 5, I'm at my next point of negative 2. Use a similar logic for your y values. We're starting here now at negative 5. And I'm going from negative 5 to positive 2, so I'm adding 7. So think about your slope is plus 7t. In this case, they will give you some directions for t. For t, usually you want it to start at 0, because when I plug in 0 here, we get our starting point of 3, negative 5. And then it's easiest just to make it end at 1. When it ends at 1, all of a sudden when we plug in 1, we get the other 2 values. We just applied the slope. You can think about that slope of 7, right, going up 7, and to the left negative 5. Left 5 will give you the next point. The circle, we're going to use the logic we use kind of with our x is going to have to be cosine, and then y is sine. So cosine of t, sine of t. Okay, here, since it is a circle, we're going to look at our radius, which if it's equal to 4, the radius is the square root of 4, which equals 2. So 2 cosine, 2 sine. The one thing that's a little different, think about how that shifts it. If it's x minus 1, that really makes it go right 1. So I'm going to go ahead and add 1 here to represent those x values. And those are the equations. It does specify, sometimes it says like, hey, For, usually we do 0, right, for t, in this case to 2 pi, to go the whole rotation of a circle. And this one will give you counterclockwise because that is our default. If you wanted to make it clockwise, the easiest way is to make it to go negative 2 pi to 0, but there are some other things the textbook talks about. We will not have to do it though, as far as applying that. Okay, you're on to homework 26. It's your last and final one. Good